In this section, we're going to examine solution stoichiometry, which is an extension to the idea of stoichiometry, which was weight relations in chemical reactions, to the use of solutions, for which you don't weigh things, but you measure their volume. So for solution stoichiometry, we're going to use volume and concentration instead of grams and molar mass. So here what we're going to do is we're going to use molarity, which is a expression of concentration in moles per liter. We're going to show how to determine concentration of a particular solution, if you know what it's made of. Then we'll show how do you make up solutions of a particular concentration that you want, and there's two methods for that, direct addition and dilution. And then we'll look at solution stoichiometry. In particular, we'll look at titrations. So let's first start by looking at what we've done in stoichiometry so far. The idea of stoichiometry is you can have a balanced chemical reaction, and what the balanced reaction tells you is the relationship between the moles of each reactant or product. And so the idea is if you know the moles involved in the reaction, either reacting or being produced of any of those compounds, you can figure out the moles of the others by the stoichiometric factors. So if 7 moles of HCl reacted, you would know that half that amount, 3.5 moles of calcium carbonate reacted. Stoichiometry so far also extended that to grams. And so you can convert from grams to moles of anything. It's important to realize that so far for stoichiometry, if you know any one of these things, any one of these either moles or grams, you can determine all of the others. So if you know how much mass, grams of any particular reactant or product is involved, or you know how many moles of each of either are involved, for just one of them, you can determine all those other ones via mole conversions using the balanced equation and mole to gram conversions using molar mass. And so the kind of chart we've used for that is that you get from grams of one of the components to moles of that component using the molar mass. You get from moles of one component to moles of another component using the balanced equation. And by component, we mean either a reactant or a product, any one of these things up here. Okay, so now what we're going to do is we're going to use a new measurement for doing different conversions, and that conversion factor now is called molarity. And molarity is a conversion factor between moles and liters, and that's because the units of molarity are moles per liter. And so we're going to look at a typical solution. We're going to make a 0.35 molar solution, that's how you say it, of nickel chloride. I had a typo there. And so that's 0.35 moles per liter of nickel chloride. And what that means is every 1 liter of that solution, you have 0.35 moles of nickel chloride. And there are two primary ways to use that. That's converting from liters to moles or from moles to liters. So start from liters to moles. If you have 450 milliliters of that solution, the 0.35 molar solution, how many moles of nickel chloride are there? So the first thing you always do is you convert that to liters. So it's 0.450 liters. And then you use your 0.35 moles per liter as a conversion factor. And because you want moles, you want to get rid of liters, the 0.35 moles goes in the numerator, and the 1 liter goes in the denominator. And so you multiply that through, and liters cancel, and you end up with moles. And it's 0.45 times 0.35, and 0.16 moles of nickel chloride. The opposite conversion is if you want to know what volume of a particular solution will contain a particular amount in moles. So what volume of this solution would you need to have if you wanted to have 2.24 moles of nickel chloride? So again, you always start with what you have over on the left. So it's 2.24 moles of nickel chloride. And use the same conversion factor, but here you want to get liters and you want to get rid of moles. So the 1 mole goes in the numerator, and the 0.35... Oh. Not true, I say. The 1 liter goes in the numerator, and the 0.35 moles goes in the denominator. And so that's 2.24 divided by 0.35. So you would need 6.4 liters of that solution, which is about 1.5 gallons of that solution. That volume will contain that. So this is just like, and this is the most important thing, this is just like grams to moles using the molar mass, but now we're going between moles and liters using the molarity. And so we can extend our stoichiometry chart to where we had grams of a component to moles of a component. For if you have a solution, you can go from moles to liters. And so you use these bottom calculations if you have a solution, and you use the top calculation if you have a pure substance, either a solid or a liquid or a gas. And so when you have a solution of something, you no longer use the molar mass anymore to get to moles, because you now know moles and liters are involved. So now let's look, how do you determine the concentration of a solution? This is actually very easy. The molarity, which often gets the symbol just capital M, is equal to the number of moles over the number of liters for any sample of that solution. And so in this case, we have 23.5 grams of nickel chloride. It's dissolved into 250 milliliters. So 250 milliliters converted to liters is 0.25 liters, just by dividing by 1,000. And our 23.5 grams of nickel chloride, we need to convert that into moles. And that we do use the molar mass because it's pure nickel chloride. So that's 129.6 grams. That's the molar mass of nickel chloride. So 23.5 divided by 129.6, 0.181 moles. So that's 0.181 moles of nickel chloride divided by the 0.25 liters, and that gives a molarity of 0.725. 0.725. You can say capital M, but that's the same as saying 0.725 moles per liter. So that's the concentration of that solution. If you know the moles and you know the liters, you're there. Next, we want to talk about how you make a solution. If you want to make a solution, what you generally do is you use what's called a volumetric flask. And they come in different sizes. One size is a 100 milliliter flask. And the way it works is you have this flask, and it has a line written on it. And the idea is if you fill up that flask to exactly that line, it contains exactly 100 milliliters. And so what you do is you have to figure out how much of your nickel chloride you're going to dump in there. And you're going to dump in water to get up to that line. So the problem is actually to figure out how much nickel chloride to use. And you need to know the number of grams of nickel chloride to add in, and you're going to get that from the number of moles of nickel chloride. And so your real question is, how many moles of nickel chloride do you need for this solution, which is going to be 100 milliliters of 0.300 molar. And so what you do is you need to use the volume and the molarity to determine the number of moles. And so you'll learn after a while that volume times molarity equals numbers of moles, when the volume's in liters and the molarity's in molarity, as it were. And so we have 0.100 liters times 0.300 moles per liter of nickel chloride. And that comes out to 0.0300 moles of nickel chloride. Now you can't weigh out moles of things directly because the scales don't have moles on them. The scales have grams on them because different things weigh different amounts. So you take 0.0300 moles of nickel chloride and multiply it by the molar mass of nickel chloride. That's 129.6 grams per mole. And that gives you 3.89 grams of nickel chloride. And so what you'll do is you take the 3.89 grams of nickel chloride, you'll put it in here, you'll add water, you'll mix it up, and you keep adding a little bit of water, mixing it up until you get up to that exact line there in the volumetric flask, and then your solution's made, and you know exactly what its molarity is. So that's one way of making a solution. The other way is by dilution. And here what you have is you have a concentrated solution in your lab, which is often called a stock solution. So you have a concentrated stock solution, and you're going to dilute it to get a more dilute solution and more of it. The theory here is that in our example here, what we're going to have is we're going to have some amount of 2.60 molar nickel chloride. And what you're going to do is you're going to add water to that. And when you add water to it, you're going to add enough water so that when you mix it up, it's going to be diluted to only 0.300 molar. And so what you need to do is you need to figure out the ratio of the nickel chloride concentrated solution to the concentration you want, the dilute concentration you want. The key here is that the number of moles of nickel chloride is the same before and after you add the water. So what that means is that the molarity times the volume of your stock solution, which equals the number of moles, because volume times molarity equals the number of moles, for your concentrated solution, let us say, is equal to the volume times the molarity of your dilute concentration. And those two number of moles are equal to each other because you've not added any nickel chloride. You had some nickel chloride in there, you had some water. So if you know the amount of nickel chloride you're starting with, you'll know how much you ended up with. So in this case, the quick and easy way to do this is you just use this quick and easy dilute solution method. And what you'll do is you'll take your concentrated solution, 2.60 moles per liter, times the number of milliliters you need, that's what you're looking for, is going to give you 0.300 milliliters, moles per liter. That's the concentration of your final solution, times 100 milliliters. So 100 milliliters. I reversed the volume and molarity on here. And so therefore the number of milliliters of your concentrated solution is going to be equal to 0.300 moles per liter times 100 milliliters over 2.6 moles per liter. And those moles per liter cancel, and you're left with milliliters. So it's 0.3 times 100. Can't believe I actually did that. Divided by 2.6. So it gives 11.5 milliliters of the concentrated solution. That's the 2.6 molar one. So you take 11.5 milliliters of that, add it, and then add up enough water to get to exactly 100 milliliters, and then you'll have the same solution. The key here is that what you can do is, if instead you don't want to use the quick and easy thing, you can calculate the number of moles. So you can take 0.100 liters times 0.300 moles per liter of your solution, and that will give you 0.030 moles. That's how many moles you need for your dilute solution. And then what you can do is you can convert that 0.030 moles using the concentrated solution. Say there's 1 liter over 2.6 moles, and you can get liters of that, 0.03 divided by 2.6, and that gives you 0.0115 liters, and then convert that to milliliters, so it's 11.5 milliliters. So it's the same answer. So you can either do it by passing through moles or just using the quick and dirty dilute solution method. So those are the two methods for finding, for creating solutions of a given concentration. Finally, we're going to look at stoichiometry of solutions, and in particular what we're going to do is we're going to use the idea of titrations. And the idea of a titration is that you have one reagent, in this case we'll put an acid in here, and you slowly add the other reactant, which in this case will be a base, and the base and the acid react together, and you slowly add more and more and more of this, and there's something that happens, there's some indication when the reaction is just done. So there's an end point that can be observed. Earlier on, we talked about a case where you had grams of a reactant added to a different reactant, and you were plotting grams of product. And as you had more and more reactant, more and more reactant, more and more reactant of one reactant, eventually the first reactant runs out, and you get a break in the line. The idea is that point there is the end point of the titration. You keep adding more and more base until the acid just gets used up. And the idea is you have something here that indicates that. And in acid-base titrations, it's called an acid-base indicator. And the acid-base indicator is a compound that changes color depending whether it's an acidic solution or a basic solution. So when the solution is not, when the reaction is not done, the solution is acidic and it's one color. Soon as you pass this point, the solution has excess base, because that's the stuff you're adding here, and it becomes basic and it changes color. So that's the general idea. For titration, the idea is that the reaction ends up being exactly even at that endpoint. Okay, so here's the way your lab was working. Your lab had two parts to it. The first part is you made a roughly 0.5 molar NaOH solution. But you didn't know exactly what that was because you just made it up kind of crudely. Our NaOH we gave you, which was around 3 molar, was not exactly 3 molar. It was close, but not exact. And you used crummy glassware, not very good volumetric glassware to make it. So it's around 0.5 molar, but you don't know exactly what it is. So what you have to do is you have to find out what is it exactly. What's the molarity exactly for that? And you do that using a titration using oxalic acid, which you can weigh out. And so the idea is you'll know the grams of oxalic acid. And when you react this, you'll know, or when you just weigh it out for that matter, you'll know the moles of oxalic acid, just because you weighed it. In the titration, you know they react, and so when they react, you'll then be able to know the moles of NaOH. You'll know the liters of NaOH from the titration. And you measure that using the burette in the titration. And then you just divide the moles of NaOH by the liters of NaOH. And that equals the molarity of the NaOH. Very often, concentration molarity is symbolized by putting the thing you're measuring the molarity of in square brackets. So that means the molarity of NaOH. And so in this case, we had 1.020 grams of oxalic acid. And I'm not going to write this out, but using the molar mass, which is 126, so 1.02 divided by 126.06, I think, that comes out to 0.00809 moles of oxalic acid. Then, the reaction that occurs is one oxalic acid reacts with two NaOHs to go to make products. And what's interesting about a titration is you often don't even care what the products are. You just need the ratio of the reactants. So it's 2 to 1. So you multiply this by 2 moles of NaOH over 1 mole of your oxalic acid. And that gives you 0.01018, 0.0162 moles of NaOH. So you now know how many moles of NaOH were consumed in your titration, and you measured the milliliters of NaOH, and you did that when you did the titration. You have a burette here, and you have your NaOH in it, and the idea is you measured how much NaOH when you started, the NaOH went down into your reaction, you measured how much you've got when you're done, and that difference was 23.8 milliliters, which equals 0.0238 liters. So your concentration of NaOH is therefore equal to the moles over the liters, 0.0162 moles of NaOH divided by 0.0238 liters, and that comes out to 0.680, which is actually considerably more concentrated than the 0.5. So that's it. So in part 1, the idea was you've made this NaOH solution, you're going to use it for your titrations, and you wanted to know what its concentration was, and you know that now. So actually you do that twice, and you just do the calculation twice and average them. Now what you're going to do is you're going to use your, I'm going to write that down, NaOH concentration equals 0.680 moles per liter. Now what you're going to do is you're going to use that NaOH solution to define the molar mass of an unknown acid. And the idea, again, is that you have this unknown acid. It's got a formula H2X. You don't know what X is. X isn't even an element. It's some other chunk of molecule. But some acid that's going to react 2 to 1 with NaOH. And that's going to make products. And your goal is to find the molar mass. The molar mass is, of course, equal to number of grams over number of moles. So the grams is easy to get. You just weigh out the molar mass. You weigh out the sample. So that's going to be the number of grams. You get that from weighing it of your acid. Diprotic means it reacts with 2 hydrogens. The number of moles you get from your titration. And so the idea is in the titration you use 35.2 milliliters of NaOH. So that's 0.0352 liters of your NaOH. And the whole idea is you now know how to convert that to moles, because you now know it's 0.680 moles per liter. And the whole idea of part 1, doing part 1 of the lab, was to get that number so you could use it in this calculation in part 2. So that's going to be 0.0352 times 0.680. So that comes out to 0.0239 moles of NaOH. So that's how much NaOH you had in your reaction. And now you can use that to find how many moles of H2X, because there's a 2 to 1 ratio. So 0.0239 moles of NaOH times 2 moles of NaOH below 1 mole of your H2X, whatever that might be. And so you can divide that by 2. Sorry, that's 0.239. I left out a 3 there. So divide by 2. That's 0.01197. I'll just add an extra digit there. Moles of H2X. So therefore, the molar mass is equal to the number of grams you used, 1.265 grams, over the number of moles, 0.01197 moles. 0.265 equals that. And I get 105.7 grams per mole. Which is a perfectly reasonable number. And that's it. That's how you use solution stoichiometry to determine things like that. We are done.